Welcome, everybody. Thank you for joining today's session, Data Science with Incorta. A few housekeeping notes before we begin. By default, everyone has been muted, but we have quite a few people on the call here today to make sure that if you have any questions, you can enter them into the Q&A, and we'll make sure that they get answered either throughout the duration of the session, or we might hold some of those questions to the end of the session and make sure that we sweep through and every question is answered around Data Science with Incorta. Today, I'm going to introduce two individuals here. We're going to do something a little bit different for Action on Insights. We wanted to get some experiences from the field, right? We're talking about one of our close partners, PM Square. We have Craig Colangelo joining us here, a senior solutions architect with over 20 years of experience of diverse data warehousing and analytics leadership experience, and also Chris Chen, data engineer with PM Square with over 20 years of experience. So cumulatively, you could say you put together, they got a half century of experience, and they're going to talk a little bit about their view on data science and what they're seeing within the workplace today. So I'm going to hand it over to Craig to kick off the session.
All right. Thanks a bunch, Joe. So today we're just going to walk you through just a very brief introduction of who we are and what we do, talk a little bit about data science and kind of level set, kind of some table setting sort of things, common terms so that we can kind of speak the same language here. Talk a little bit about common use cases and where each of these things kind of fit in the greater datascape, especially in the world of AI. Talk a little bit about the data science process and lifecycle. And there are many, and I'll show you just one, but get into depth there a little bit. And then my colleague Chris is going to walk us through a little bit of a demo using Incorta and showing us how he put together a pretty cool little model, again, using Incorta data. So he's going to actually walk us through and do a demo, and we'll just wrap up. So should only take about, I don't know, half hour, 45 minutes or so. And let's get into it. So like I said, just a brief intro of who we are. We're PM Square. We're a data and analytics consultancy, and we support our customers across their entire analytics journey. We've had the privilege of helping our customers build high ROI modern data architectures. And since we're an Incorta partner, we've done quite a bit of data science work through Incorta for things like propensity to buy models, market basket analysis, and customer 360. So with this webinar, we really wanted to make sure that everyone understands just how accessible data science tasks and initiatives are using Incorta-based data and the Incorta platform itself. It really is insight, right at your fingertips. So let's start by just briefly overviewing and level setting on, what really is a very broad topic of data science. It can mean a lot of things to a lot of different people. So many of us have seen analytics maturity models like this. They've been around forever and convey different things, but each circle kind of represents a categorization of type of analytics. So reading it from left to right, we can see that each evolution kind of adds greater competitive advantage. Now, each type doesn't necessarily build upon the previous, but there are usually kind of synergies and natural progression from one to the next. And it's important to note that when using this sort of model to gauge your practice, not to let future-looking analytics work devalue in any way those initial categories around understanding the current state, which is absolutely foundational. So solid BI work and data engineering work enable the future-looking data science and predictive work. And that's what we're going to be talking about today. But we found that many organizations experience a natural stall point when they're trying to move into the advanced analytics categories, because, right around here, this often it takes you from, squarely into the realm of data science and everything that goes with it. So that's what we'll be discussing today and showing, and it lands definitely squarely in the advanced analytics space and is considered data science. So we're going to show you how PM Square and Incorta get you there into that sweet spot of high competitive advantage using base data that you likely already have, a tool that you likely already use, and building upon the data engineering work that you've likely already done to provide analytics to your organization. A lot of ambiguity again, but simply put, data science is the practice of analyzing data to improve decision-making. So if you've been around as long as Chris or I have, sorry, Chris, you probably remember being part of a group at one point or another called something like decision support or something similar, right? And, truly what's old is new again. So curation and presentation of data is certainly important, but ultimately it should serve to support decision making. And that's really what the core of data science is typically all about. Now, in the world of data science, this is done using statistical inference to answer questions via explanation. Often, those are yes or no Boolean sort of answers, or to make a prediction. So those are really the main types of data science models, explanatory or predictive. And probability is always at the center. And it's the aim to make a statistical inference to a population from a sample set of values. So let's quickly talk a bit about the greater data science datascape here. There's a lot of ambiguity in the terms here, but at the end of the day, they're all related and often lean on each other in different ways. So exacting vernacular aside, data science is really the foundational piece. It's all about organizing and analyzing data to gain insight for human decision-making. Really, it's about uncovering and illuminating issues, solving complex problems, detecting patterns, and things like that, all for the purpose of gaining insight. And it definitely leans on inference and requires human intervention. It's been accurately said that data scientists are more like an organization's truth tellers than they are software engineers. Let's talk a little bit about machine learning. It's kind of really a subset of data science, and it's utilized by AI. It enables computer algorithms to learn from data and models, which is really the most common form of AI. And it also requires human intervention. It's a tool basically used by data science to implement insights. And then, of course, when we use the term artificial intelligence, these are computers and machines demonstrating intelligent behaviors, things like learning capabilities or being self-aware, which I don't think has happened yet, but we'll see. For common or more broad usage, it's really more about learning and performing certain tasks that imitate human behavior. So AI is also a tool used by data science to implement insights and to improve machines in more automated ways. Broadly, though, there's plenty of data science, machine learning, and AI in play in our daily lives. Some common and kind of broad use cases here for data science include things like classification efforts. If you think of diagnosing heart disease or skin cancer predictions using indicators, or machine learning models that can distinguish between normal and potentially fraudulent bank transactions. Those are some examples of classification. Recommendation engines, things like Netflix movie suggestions or online dating matches. Prediction engines, these can be things like propensity to buy or churn, or predicting just-in-time inventory levels. And things like image recognition. So these can be things like facial recognition or photo classification, which is kind of more on the deep learning AI side of things. But it's definitely true that anyone who's ever tried to assemble a team or a resource who has, real data science chops, they've found out that data science skills definitely crosses boundaries, and the needs really vary, especially depending on your type of organization. So we found that higher learning entities and medical data science are often more kind of conventional statistics based, whereas more, traditional business entities kind of have they typically have fewer standards around like statistics, and there might be a greater opportunity there for creativity in the data science process. But regardless, skills often include conventional statistics, which is kind of the grandfather of it all. Various technical skills like Python, R, Scala, SQL, and lots of other smaller things. And subject matter expertise in some way, shape, or form around the data domain that you're analyzing and modeling. At the end of the day, data science is, like most of us, or in most of the things we do in our normal lives, part art, part science here. And boiled down, there are generally three key role families with kind of complementary skill sets involved in data science. You typically have your data analyst type, your data engineer type, and your data scientist type. So a data analyst might center around exploring the data to figure out which data potentially supports a business problem, whereas a data engineer is kind of more focused on prepping, cleaning, flattening, producing high quality, consistent data And a data scientist is often involved in curating and consolidating for that specific data science purpose data, and then, of course, building and training and testing their models. But they all often need very real technological breadth and depth. So there are definitely different tool sets, different soft skills, and different focus for each of those role families. But the truth is that that's somewhat reduced, though, by using an entry point and a common starting platform like Incorta. So now when it comes to finding like a data science resource, people, hiring managers often look for these like data science unicorns. And that's kind of the dream, that there's this special sort of resource who is super skilled in all of the role families that I just mentioned, enough to be kind of an all-in-one data science shop unto themselves, right? So, unicorn implies something, doesn't it? What often happens is that a hiring manager, finds somebody with some decent data science skills, and then they have them manage all of the, data science and periphery resources themselves, or the entire data science practice on top of it, right? So whether or not these people, want to actually manage others, and whether or not it's even a good fit, oftentimes it's not. So these sort of approaches are mostly, whether it's the unicorn or the, hey, I've got a great data scientist and now I'm going to make them, a manager of the practice or the people. These sort of approaches are truly, really mostly pipe dreams in our experience. They all have very different sort of career paths, though they're interrelated. So it's important to kind of recognize the three distinct roles. Oftentimes too, there's also another team involved in operating models once they're in production, that are more skilled in the IT operations side of things. They kind of assess, maintain, and monitor the prod models once they're out in the wild. And that team is often called ML ops, machine learning ops, depending on the size of your organization. But they ensure models are relevant over time, which definitely takes tinkering, and that they're being used, and that they're alerting data scientists when confidence levels drop or when the data shape changes. So the truth is that all models degrade over time, and you need to have someone monitoring that degradation or drift so that you can actually adjust it. So there are several ways to go about depicting, a typical data science cycle, and this is really just one of them. Most of these stem from the CRISP-D models published a couple of decades back, but some projects kind of demand agility and focus more on the data, while others require more rigor and take more of a comprehensive approach, spending more time up front defining the problem, working each step, and then working with the users on deployment and consumption methods. But generally, iterative agile steps are usually much better than a linear sort of waterfall approach here. So again, the steps and approach might vary, but they always start with a problem in mind. So you should definitely spend time stating it, which is sort of more implied in the model that we're looking at here, but it is universally true. But once the analytics problem is properly stated, you should generally ensure that the insight that you hope to bring using this data science project will result in concrete decisions by the business. That's what this is all about. It's about better decisions through predictive data. So make sure that there's a plan for how to use the data, or how to use the insights that your data science project is going to deliver, hopefully. On the gather step, this is really all about identifying, it's kind of where we start typically after identifying the problem. And it's really about identifying the data. It's a really important early step. So, really without data, you won't be able to start. So do you understand the data that's applicable to the problem scope? And its corresponding domains? Do you have access to all of the data? Is it in a place that you can actually use it? These are all questions that need to be answered early on. Exploring and cleansing. These steps involve ingesting, profiling, understanding, making the data usable, essentially. So areas of importance here include, documenting the data quality, cleansing the data. The principle of garbage in, garbage out certainly applies to data science models. Combining data from different sets, ensuring it meets the needs of the model, and then of course gut checking it early and well with the stakeholders. This is kind of the building the foundation and frame of the house sort of work. On the build the model step, if the data prep is the foundation and frame, then building the model is the interior decorating, right? This is the part where You decide on the modeling techniques and the algorithms. And when you do multiple passes of feature engineering and reduction, and ultimately get to a statistically relevant propensity or probability score. And when we talk about statistical relevance here, we're talking about a p-value of less than or equal to 0.05. So, it's creating the model in a way that allows stakeholders to gauge the model's efficacy with minimal cost. Think like MVP sort of an approach here, most viable product or a minimum viable product. And of course, the business should, like I said before, the business should really know exactly what they're going to do with the data, decision-wise. With these results, once your model starts to, shed light on the problem. Next up is to deploy and apply. So once it's deemed useful and prod-worthy, it needs to be deployed into production, visible and used, right? So this can mean many things, but without it being in a decision maker's hands, really what's the point, right? Once in the wild, it should be reassessed, extended, enhanced, improved based on results and empirical use. And then, of course, the term AI explainability kind of comes into play here, right? It's certainly becoming more relevant by the day. But having ethical, transparent, explainable models helps build trust and understanding. There are certainly highly accurate black box methods, things like XGBoost and neural nets that are much harder to explain and don't really lend themselves well, for like layman's understanding. But whenever you build a model, if you can incorporate explainability into it, you generally should. And of course, notebooks themselves they lend themselves well to that goal. Just the nature of the code and text all kind of in one here, being able to explain it in a stepwise sort of a way. But generally, though, there are usually trade-offs, and these sort of expectations and decisions around transparency, really should have kind of occurred earlier when the project is kicking off. But one of the biggest hindrances in the data science space, other than the availability of data in general, is that something like 80% of data scientists' time on a project is spent broadly on data prep. So things like discovering, understanding, ingesting, integrating, profiling, things like that. The other 20% is spent on actually building the models, managing and improving those data science initiatives. And worse yet, nearly 80% of data scientists don't even enjoy that sort of work. So things like AutoML, they kind of help a bit, but that percentage of time spent on data prep never seems to decrease. It's a bit of a paradox in that sense. And a lot of it does stem from the fact that data scientists will never run out of things to try with the data if the data is prepared properly. So there seems to be an opportunity to do better with the tools and resources that we already have in order to free up valuable data science time for full-on data science work. And guess what data engineers are great at? Data engineering, right? So if you had the right tooling in place, some of it could actually even be an easy ask, right? If we have the opportunity to provide a better starting point for the data, it just frees up data scientists to do more of the data science specific data prep work. So it's true that some of the data prep, quote unquote data prep work as it relates to data science is just an absolutely core piece of data science in the form of feature engineering, right? And data scientists can't and wouldn't ever want to get away from that, but lots of it can be performed better, or it can be bettered before the feature engineering work even begins, right? And that's kind of the value prop for things like Incorta as it relates to data science. So this is where a unified data access platform and maybe a data ops practice come into play. So providing high fidelity, high quality, and ready data to the data science process shouldn't start with the data science ask itself. It should be, and often is to varying degrees, part of existing data engineering and analytics work that are likely already being done in your organization. So speaking of tooling that makes data science prep a little bit easier, we found that Incorta has some really natural advantages when it comes to data science data prep. So much of Incorta data is normally third normal form transactional data at its atomic level with full fidelity, and it's often just what data scientists need to support many data science use cases. And oftentimes there's really no need to deconstruct aggregated views or complicated data pipelines. You can start at the bottom if necessary, or at a more curated sort of an entry point if of benefit in a typical Incorta environment. The Data Profiler app, which is available in the community. I think I think Chris is going to touch on that a little bit in his demo. It makes it easy to understand and profile your data source candidates so that you can do all the early work in the data science cycle with ease. So things like, understanding zero values and missing values and uniques and duplicates and outliers and things like that, which, outliers aren't necessarily things you want to discard right away. Sometimes they add a whole lot of value. So understanding and handling those sorts of things early is really what that data profiler is all about. And then, of course, the native data cleansing and combination capabilities in the Incorta tool allow you to pull together data in exactly the way that you need it. So, it's streamlined, it's purpose-built, but without all the complicated tools or methods. Then once you're, more downstream and you're starting to do some of the data science specific work, when that stuff needs to begin, you've got integrated Apache Zeppelin notebook environments, which of course support things like PySpark and R and Scala and Spark SQL and things like that are available within Incorta. And they also have a notebook add-on service, which runs your notebooks in an application in Apache Spark. But Chris will show some of that here shortly. So Chris, I'm going to stop sharing. And with that, I'm going to hand it over to you so that you can take us into the world of data science in Incorta and show us a bit about how it's done.
So thanks, Craig. So at this point, I'm going to show you how the data science cycle is supported by Incorta, and then I'm going to show you a small data science project implemented in Incorta. Let me move on to my okay. So the standard data science tools, the typical data science project is run in an Apache Spark environment with Spark as the computing engine. Python's PySpark library is used to handle the data, and other data science specific Python libraries are used to crunch the data, and the Spark environment is used as the computing engine. In Incorta, as Craig mentioned, the Python scripts are developed in an Apache Zeppelin notebook, and some developers can prototype their code in the standalone Jupyter notebooks on their local machines, but Spark environments are typically a lot more powerful, hosted on servers or in the cloud. Incorta supports data science by the Incorta Direct Data Model data engine is in fact based on Spark. You can create your scripts either with Spark SQL or PySpark. In materialized views, you can either do it as a single query or develop in the interactive Zeppelin notebook, and then present the data as if a typical SQL statement was being used. Incorta has also extended some of the Python libraries with Incorta specific functions, such as reading and writing to Incorta tables and displaying data inside your Zeppelin notebook in HTML tables. Sometimes it's difficult to have to show a data frame with a large number of columns. And if you use the extension to display in HTML tables, you can scroll to view your data back and forth and up and down. So now what you've all been waiting for, the small sample project that illustrates data science in Incorta. So let's pretend that I am a realty, that I am a new agent for a realtor in the town of Ames, Iowa. The housing market is hot and my realty agency wants to capitalize on it and fast. My week-long training was conducted on a Monday. I've been given a jacket with the realtor's logo, a login to the local MLS system, the URL of Zillow, some printed listings, a few cell numbers of my buyers, and get out there and get them, kid. So the MLS system, the local system, has descriptions, facts, and history of previously sold and currently selling prices, properties. Zillow, of course, has some of the same information, but it is available to anyone. So I have access to all the local properties and their prices, but how do I know that these prices are valid? What's a good selling price for my seller's properties? What's a good price for my buyers? With all of this info that everybody has, how can I gain an edge? And I would use data science. So as Craig mentioned, the cycle of data science is gathering, cleansing, modeling, and applying. So I am going to start with the gather process. I extract all of the important property information from Zillow and MLS, house styles, number of floors, bedrooms and bathrooms, sales prices, and I can either extract that in an Excel or CSV file, or if I can, connect directly to the database. Then I go through cleansing the data. The unique property ID doesn't really help me because it's 100% unique values. Are there that many houses that have no bedrooms or bathrooms? Can there be a driveway with no garage? This particular house isn't even in Iowa. All of the lots are flats, the kitchens are above ground. They're all wired for electricity. They all have roofs. So I'm going to change the data to group values that occur infrequently. Practically all properties have electricity, but some of them in rural areas might not. So I might group those together. They could be that particular column could also be could be highly skewed. And there might be some cases where the data is noisy because there are a large number of null values. To model the data, I start by splitting the sold houses data that I've gathered, and I split it into two sets, a training set to build my predictive model and a testing set that will help me verify the results of that model. Based on the analysis of the data that I've looked at, I choose a particular algorithm to create my model using the training data. And I use that model to predict sales prices for that training data, for the test data set, and compare the results. And I might have to change things, either add back or drop some columns, or perhaps even change my statistical algorithm. Now that I've got my model, I apply that to the properties that are on sale, my target, and I get the property ID and the predicted sales price, and I identify the best deals. I can give my buyers directions to the best priced houses, and if I need to, I can help my sellers adjust the price of their houses to the best market price, and the result of that is profit. I have lots of purchases and sales of houses. My commissions grow, and I buy the realty agency. And today it's Ames, and tomorrow I take over Iowa. So now let's go through a demonstration. I will show you what I've built in Incorta. So I'm going to, in the gather phase, I'm going to pull my data as local files. And I have a CSV file of properties sold and the CSV file of properties that are on sale. If I go to my schema tab and I open up my folder, I have two tables with the sold and on sale, and I can show you, preview the data. I have multiple columns. In this case, I have 1,460 rows, so that would be 1,460 properties. They're encoded. I have lot shapes, I have utilities, I have external quality, and then at the very end here, I have, because this is property sold, I have the sale price. Similarly, I have the properties on sale. I have the same columns. I have the same number, a similar number of rows, 1,456. And I have the same columns, except on the very end here, I don't have the sale price, because that's what I'm looking to predict. Now, one of the ways that I can do some cleansing of that data is to do it in a SQL statement. Spark supports what's called Spark SQL, where you can create a query in the Spark SQL, and so in this case, I'm taking the columns and I'm decoding the MS zoning field. So it's going to come through as A, C, I, and RH, etc. And because I have a data dictionary, I know that A is agriculture, etc. And at the very end here, because I'm going to be showing this in a table, I have the property count as a 1. So if I go into my notebook, which I'm using in Spark SQL rather than in PySpark, I run my query, and I can actually, if I want, display the data that came from the query in tabular form. So at the very end, I have my sale price, because this is the property sold, and I have a property count field. So I can do, if I want, within Incorta in the notebook, I can do some mapping, I can do some graphing. So I have the zoning description that I created, and I'm going to grab the property count as the values, and I'm going to do it as a count. And now I have a graph here of the property, the zoning property description, excuse me. And because that's a little bit difficult to view, I can rotate it, the label, in 45 degrees, and I have now low density residential properties. There's 387 of them, medium density, and others that occur a lot less. And if I want, I can actually drag a field in here to do some grouping. So I'm going to do the building type, and I'm going to drag that in there, and it's going to modify my graph, my bar chart. So now I have counts of residential, low density, medium density, etc., broken out by family, 1-family house, 2-family converted, duplex, townhouse, etc. So that's one way I can profile the data and check to see if I have what I'm expecting, and also do some modifying, do some cleansing. So let me get back out of that. Despite the usefulness of that, I'm going to skip that, and I'm going to do the cleansing in a Spark Python materialized view. So look at my property sold. I create a materialized view called property sold cleansed, and I open up my data set. and my materialized view, I can have the entire program, the entire script be in a single query. And I might copy this and for reference later. But what I really want to do is do some development in a notebook, because a notebook is divided into multiple paragraphs, and each paragraph can be run individually, and they can depend on what's above what's been run previously. So here I'm importing the libraries, and I'm using one of the Incorta extensions to the machine learning library, and I'm reading from the webinar schema, the properties sold database table. Now, I'm using one of the standard data science libraries called pandas. And what I can do in Incorta is convert from a Spark data frame that I've retrieved and put it into a pandas data frame. And so I'll show you that my variable is df for data frame, and it's a pandas data frame, and I have 1,460 rows and 81 columns. And here's the list of all of my column names, all 81 of them. I've already done some analysis, and I know that these particular columns aren't useful to me, but I will show you. So these are the columns that I have remaining, 42 of them. And these are all the columns, but it's kind of difficult for me. These are the first 10 rows, but I know because I have 40 plus columns, it's going to be difficult for me to view these. What I can do is, so I'm going to get back to that. Looking at the columns, I noticed that I have basement full bath, basement half bath, full bath, and half bath. The data that I've gathered does not have a total number of bathrooms, which is more useful to my buyers and sellers. So what I'm going to do is identify all those columns, and I'm going to calculate a total number of bathrooms, multiplying half bath by 0.5 and adding full bath and full bath, basement full bath. And the next paragraph, I see my columns that I've used and the results of the total bath calculation. And then because I don't need these columns anymore, I'm going to drop them. Now, if I've done my cleansing here and I've completed, and I need to convert this back into a Spark data frame to save it to an Incorta table, I need to know the data types of all of the columns. So I grab all of the data types and I put it into the structure of a Spark data frame that I'm going to use to do the conversion. So I take things that are int64 and I call them the Spark integer type. If it's an object in pandas, it's a string type. And things that are calculated because my bathroom value has half bathrooms, so it's a double. And then I can create another Spark data frame using the schema and the data frame variable, and I convert that to the Spark data frame. Here's another function that was extended into the machine learning library by Incorta. It's the Z show, as I talked earlier about displaying data in a tabular form. Whereas before I had the issue with too many columns, and Spark it shows the first 4 and the last 4. Down here, I can see all of the columns that I was looking for. all the way down to the total bath that I calculated. And then I save that to a Spark. Save that with a Spark data frame, and this is going to be the results of my materialized view. So I have all my columns, including the calculated total bath. And so here's another view of that, and my total bath. Here's a profile, some minor profiling. The minimum value of total baths is 1. There is someone who has a property with 6 bathrooms. So that's my cleansed data for sold properties. I have something very similar to the properties that are on sale. The difference is that in the data, I have calculated the total number of baths, but there is no sale price because I'll be predicting that. One moment. Okay, so now that I've cleansed my data, sold and on sale, I'm going to go through and do my predictions. So the results of my predictions are going to be a property ID of a property that's on sale and the predicted sale price. The code for my materialized view. Once again, I can, in the full query, I can have all of my entire program scripted in there. For my use, I also put a number to each. I put a number for each paragraph in the notebook. So when I if I save the query into a single file, I know which script is in which paragraph. So I import my libraries. I import my properties sold cleansed because I'm going to be using that as my source for my predictions. So I have 1,460 rows and 39 columns, total baths and sale price. Now what I'm going to do here is I'm going to split this into 2 variables, essentially the x-axis, which has everything except the sale price, and the y-axis, which is the sale price. I'm going to take that x-axis and split it into a training set and a test set. If I want to make sure that each time I split it, I get the exact same the split values, I can use the same random state value here. So if I make this 1, each time I run it, I'm going to get exactly the same split. So I've split it into xtrain and xtest, and I have 1,095 rows in xtrain and 365 rows in test shape. Now here, what I'm going to do is what's called converting text columns to numeric columns. Now, when I showed you the data before, there were some columns that had text values in them, like the RH or the RL for the properties, property types. Now, what I need to do, because my algorithm can't calculate on text values, I take that, converting it will take each column, will take each value in that particular column and split it into multiple columns, and there'll be a flag in each column whether or not that particular property is true or false for that value. So this first property here has residential low density. So it's got a 1 in the MS zoning RL column, but a 0 in all of the other ones. And I'm doing something similar for all of the rest of the values, all the way to the end of sale condition, either family, normal, or partial. Okay, so I've converted that data set. And I'm going to do the same to the test set. I'm going to encode that with converting it to numerical columns. So I have X train encoded and X test encoded. And I showed you those values in the table for test encoded and training encoded. Now what I'm going to do is I'm going to align the training and test data sets to make sure they have the same rows and columns. So when I finish, I'm going to have all of the same columns in the same order in both the training and test data sets. I'm going to save those into train encoded final and test encoded final. And I'm going to go through and scale these data sets. Now, scaling the data set is what you do to transform your data so that its distribution is the same across all of the columns. You have a mean value of 0 and the standard derivation of 1. The lot, for example, the lot area that in the data is from 0 square feet to 56,000 square feet, but the square feet of the first floor of a house could be anywhere from 400 to 5,000. To do the analysis, we have to adjust each column so that they all have the same scale. So you're essentially removing the units between the columns. After I've done that, my looking at the data and understanding of it, I'm going to be using the random forest regression algorithm to do my final predictions. So I create an empty random forest model, and I use the X train encoded scale to predict my training, to predict on the training data set and return the sale prices. That's in there twice. And then I'm going to compare the predicted sale prices for the test data set to the actual values of the sale prices in the test data set. So I do some validation. I'm getting the mean absolute error and the mean squared error, in this case the square root error, and that's coming back at 28,000. So I can improve on that. What that's saying is that my predictions are about $28,000 off. I would probably do some adjustments to improve that. But for this, I'm going to deem that as a good enough value. So I'm a good enough model. So I'm going to continue by predicting the sales price for all properties that are sold. I'm going to convert the text columns, scale the properties, and do the predict the sales prices for all properties that were sold. So I have my model now, the RF model on full data. I'm going to use that on my properties on sale. So here I'm going to retrieve the properties on sale cleanse data, and I'm going to convert it into a pandas data frame. I'm going to call that data frame on sale. So in the original, I had 1,460 rows, and my encoded split it up into 173 columns. The new one that I'm getting is 1,456 rows with 38 columns. And I'm going to run through and do that encoding where I split the columns. And now I have 165 columns. So I have 173 and 165. So I'm going to adjust both of them, both of the data frames, so that they have the same number of columns in the same order. So you'll see that my final training data and my on-sale final data both have 173 columns. I'm going to scale that data, and then I'm going to use the RF model on full data to predict the sale prices for the on-sale data set. So I have 1,456 predictions. I'm going to create a pandas data frame with the ID of the property sale, or properties on sale, and the sales price prediction for each property. I'm going to save that in a Spark data frame, and then I'm going to save that as my materialized view values. So I have the single column and the 2 columns of ID and price. And you can see I have 77,000 to 395,000 in predicted prices. Just to show you what I have, what I can do with that data is I have a properties dashboard, and I have 2 tabs, properties sold and on sale. And I can show you the average sales price and the number of properties for each property and style and type. So I have duplex, single family, 2-family conversion, etc. And the decade it was built, number of properties, and average sale price in tabular form. But I also have it here in graph form. The number of properties on this scale here, 1890s, built in the 1890s. There's 15 properties there, and the average sale price of that is 180,000. All the way to the 2000s and 2010s, where I'm getting my average sale price of 394 for for just one property that was built in the 2010s. And I have my raw data here for other analysis. I also have a similar dashboard, similar tab on this dashboard for properties that are on sale, built in which decade, number of properties, and the average predicted sale price. And I have also a similar insight showing the number of properties and the average property sale price for things that are built in a particular decade. Average sale price for houses in the 1950s, built in the 50s, 172 of them, average sale price of 137. Now, this is a very simple dashboard. If I wanted to do more analysis, I could take the predicted data that was the houses that were predicted that were sold, and take that predicted price and do some analysis to see. When I said it, there was 28,000 a mean of 28,000 in the difference between the predicted prices for the test data set. I could do some graphing to see what the difference is for each individual one, plus and minus. And there are some other things that I could do as well, but at this point, I'm going to throw it back to you. To you, Greg. I hope this was useful to everyone, and I appreciate your time.
Awesome. Thanks, Chris. If you want to stop sharing, I'll quickly share a screen.
Stop sharing.
Thanks. So just wanted to make sure that everybody knows that that you can find Chris's script out on the Incorta community site at community.incorta.com. Just look for Chris's username cchen-pm2. He'll post it all out there. I think Incorta, Emma, you're going to send out, you're going to send out an email with a link to the slides, and I believe we'll also be posting it to the PM Square YouTube channel, so you can find it there as well. Joe, did you have anything else you wanted to add?
Yeah, just two questions from the audience here. First of which, this is probably for Craig. Python or R for data science, which is better?
Yeah, the age-old question. Both are definitely great. The truth is that, you know, as you saw with Chris's demo here, like, you know, everybody uses multiple tools and multiple languages in the data science world. But, you know, I mean, I have a stats background, so R is what I typically tend to use. But, and you kind of see more people with like academia or stats background using R. And maybe more like machine learning types or object-oriented programming background people coming in with Python. But, you know, they both have a very large market share in terms of, you know, data science and machine learning software and languages. But I'd say Python probably has more steam right now. But KD Nuggets is a great resource, a data science resource that we can all use to, you know, find out what's hot and what's not in the data science world. And they usually have blog content around that. You can check that out, KD Nuggets.
Perfect. And we got one more. Maybe we'll go with Chris on this one. Can I install other Python data science libraries in Incorta? And you might be on mute, Chris.
I thought I had that again. So yes, you can do that as long as they're compatible with the standard pip installation process. If you're going to do it on premise, you can connect to the console using SSH and install it on the command line. For instance, you would use pip install TensorFlow. If you're doing it on the cloud, you'll have to go to the cloud console and open up one of your clusters and go to the configuration area and scroll all the way to the bottom for Python packages. And you can add a new package there with the same name that you would use in pip.
Perfect. And I think that's all the questions we have. Thanks again, Craig and Chris, for sharing your insight and expertise today. Everyone who's on the call here, thank you so much for joining today for this Action on Insights, and we'll see you at a future session.
Thanks, Joe. Take care.